All right. Okay. So, I like doing problems together. I like having an opportunity for you to do some problems. And so there are a couple of problems scattered through this lecture. I'm going to, give you a few minutes to work on those sort of on your own, and then I'll step in and do the example just so that you get an opportunity to try things on your own before we go through it. Right, so here we go. Okay, so we are interested in chemical kinetics in this chapter. Chemical kinetics takes a look at sort of how fast different reactions occur. And a lot of the kinetics of a reaction is based on what the reactants are. A lot of it's based on temperature, which we'll talk about towards the end of the chapter. And then a lot of it is based on just the size of the molecule. Larger molecules tend to interact a little bit faster than smaller ones. It just depends on the situation. Okay, so chapter 13. Just a second here. Sorry. All right, chapter 13, here we go. So, chemical kinetics is based on a couple of things. The first of those being thermodynamics, which we talked a little bit about in chapter 6. Chapter 6 was titled thermochemistry, but it ties in nicely with thermodynamics. And the question that thermodynamics asks is, does a reaction occur? Chapter 17 for us is all about thermodynamics, and when we get there, we'll be able to answer that question better about how we know whether or not a reaction is going to occur. For example, water breaking apart into hydrogen and oxygen, right? That doesn't happen spontaneously, and thermodynamics tells us that. But other reactions do happen spontaneously, right? Iron reacting with oxygen in the air to form rust. Is a spontaneous reaction. And so thermodynamics tells us whether or not a reaction takes place. Kinetics tells us how fast does a reaction proceed. Okay. And so to look at that, we're going to use something called the reaction rate. Right? That's how we talk about how quick something is. And the reaction rate is the change in concentration. Oops. Is the change in concentration over time. What unit do we really like to use for concentration?
Moles.
That's amount. What about concentration? It'd be moles
Molarity.
Molarity, moles per liter. And so when we talk about reaction rates, we're going to talk about things in molarity, which is moles per liter, how that concentration changes over time. And of course, for time, we're going to use seconds. Now, if it's a very slow reaction, we might talk about molarity per minute or molarity per hour, but usually these changes occur pretty quickly. Okay. So for a generic reaction of compound A forming compound B, right? Just a very generic reaction. The rate is equal to, now the concentration for A, is it increasing or decreasing? If A is a reactant and B is a product.
The concentration of A is decreasing.
Yeah, absolutely. The concentration of A is going down. And so we always want our rate to be a positive number, right? And so because of that, and the concentration of A is going down, we have a negative sign out front. And so it's the change in the concentration of A over time, change in time. I don't know if you've seen those brackets before. Right? And so brackets indicate concentration. Right? And so the rate is equal to the negative of the change in concentration of A over the change in time, right? And I'll just put in parentheses here, negative, because it's a reactant. Reactants are used up, and so their concentration goes down. Products, on the other hand, are formed, and so the change in the concentration of B is a positive value, since it's a product. Now, because we only have A and B, and because it's a 1-to-1 ratio, these rates have to equal one another, right? They have to equal each other, so equal and opposite in terms of those rates. We'll talk about some more complex rates here in just a second. So if we were to graph this, right, scientists like to put things visually. If we were to pop this in a graph, oops, sorry, too far. If we were to put this in a graph, right, we would see something like this, where our A molecules, we start off with a whole box full of A, and those go down over time. We start off with no B in our box, and that increases over time. And so this is 60 seconds, so this is a 1-minute timer, right? And we could go through and count it up and figure out what the rate is. But again, the rate, because A is going down, the rate is equal to negative change in concentration of A over change in T, and the rate is equal to positive change in concentration of B divided by change in time. Okay. All right. And so, where does this take us? What do we do with this? Well, when we look at a particular reaction, this is bromine reacting with a compound called formic acid. That bromine breaks down into bromide ions, as well as some hydrogen ions and carbon dioxide gas. Over time, if we look at the solution, as we look at the solution here, the color goes away, right? So bromine is a dark liquid, right? This is sort of a reddish brown liquid. And so we mix it with a little formic acid, which is colorless. We have this darkly colored compound, and it goes away, that color goes away as the bromine molecule, Br2, breaks down into Br minus, which is colorless. And so this is what we were going to do in lab next week. We're going to take a look at a colored solution like this as it changes over time based on the reaction rate. okay? And so here we have a graph, a very similar graph, time versus the bromine concentration. And sometimes we talk about rate as being an instantaneous rate, so at a single point, right? So these are instantaneous rates. So obviously at the beginning of this reaction, that reaction is going to go faster because there's a lot of everything. As we have less and less Br2 and less formic acid in our solution, that reaction is going to slow down a little bit. It's going to take longer for that bromine molecule and that formic acid molecule to find each other in solution when their concentrations are lower. And so these rates are going down. Here it's about 3 × 10⁻⁵, 2 × 10⁻⁵, 1.5 × 10⁻⁵. So they're going down with time. Now we could also calculate the average rate. And so the average rate would just be the final minus the initial. So we could do that very quickly here. So that would be how much of our bromine did we lose? 0.0296 minus 0.0120, right? Final minus initial divided by my time, 400 seconds minus 0 seconds. And because this is a reactant, we're going to have that negative sign out front. So we can plug that into our handy dandy calculator. 0.00296 minus 0.012 divided by 400. And that negative sign takes care of anything, so we get 2.26 times 10 to the negative 5 molar per second. And so that's our average rate. Notice that none of these instantaneous rates match that. But that gives us an idea of the rate over time rather than any single instant in that reaction. Okay. All right. Now, if we were to look at this table right here, this is the table of all of the instantaneous rates. So we looked at a couple of these on the previous slide, but this table has all those instantaneous rates on there. And we can see that there is some relationship between the rate of this reaction and the concentration of bromine, right? That relationship is graphed here, and we see that it's linear, which is great. Scientists like linear things. It's easy to fit linear data with a trend line. And so this rate and this concentration must be related somehow. And so we're going to use the symbol K, which is sort of a generic symbol for a constant, and say that somehow, Br2, say that somehow that rate and the concentration of Br2 are related to one another. If we rearrange this, we can figure out what the value of that constant is, right? That is the rate divided by the concentration of Br2. And we call this little lowercase k, we call this the rate constant. The rate constant. Now, if we do this at a couple of data points, you'll see in this column here, they've done it for all the data points they took, but it stays pretty much about the same all the way through. It's constant, right? It is a rate constant. And so for this particular reaction, K is equal to 3.50 times 10 to the negative 3. And remember that the units on our rate, I'm going to put some big brackets here. The units on our rate are molarity per second, the units on concentration molarity. And so we're left with just per second. And so the units here are 1/2, which we sometimes write as seconds to the -1. A little foreshadowing. This is what we call a little foreshadowing. This is what we call a first order reaction. Because it just gives us a single per second as our unit, and it gives us a nice straight line concentration versus rate. All right, so moving along, if we look at another reaction, here we have the reaction, the breakdown of hydrogen peroxide, H2O2, into water and oxygen. Okay? In this example, they're using a device called a manometer to measure the pressure difference using liquid mercury. I don't know whether or not you discussed that in chapter 5 and 123. I did not talk about that. And so it's just a way of measuring pressure, and it measures pressure based on the amount of mercury that the reaction displaces. In any case, if everything that we're interested in, the oxygen in this case, if it's a gas, then instead of measuring the concentration over time, we can measure the pressure over time. Right? And so if we measure pressure over time, we know how to go from pressure to moles, PV equals nRT. And if you rearrange this to get concentration, so the concentration of O2, remember that's moles per liter. Which one of these 5 variables is our moles, PV, N, or T?
N.
Moles, yep. So concentration, moles per liter, moles per volume, N over V. If that's what we want to get on one side, then we just have to rearrange everything else. Right? And when we rearrange everything else, we get P over RT. And so the change in concentration of O2 is related to the change in the pressure of O2. And so we get our rate, now this is for gases only, our rate here is equal to, if we write it in terms of concentration, the change in O2 over time, and we know that the change in O2 is equal to this P over RT. Now, R, of course, is a constant, and T likely is not changing over the course of the reaction. And so if we assume that the temperature is constant, then we can take that out and we get 1 over RT. So we pull out those constants, and then what's changing is the pressure, and of course we need our delta T in the denominator. Why is this value positive and not negative? Why didn't I put a negative sign out front?
Because it's a product.
Absolutely. O2 is a product, and so I don't need that negative sign for my rate. And so let me just be clear, this is for gases. All right. So if we look at reaction rates and how that relates to stoichiometry, everything that we've looked at so far has been a 1-to-1 ratio. We haven't had to deal with any coefficients on our reactions. And so let's say instead that of A going to B, we have 2A goes to B. That means that 2 moles of A go away for every 1 mole of B that shows up. And so now we're going to write our rates a bit differently. Now, it's still, A is still a product, and so we still need that negative sign out front. But we put the 1 over the coefficient first, delta A over delta T. Now that rate has to be equal to the change in the concentration. Oops, I missed my concentration brackets. The change in the concentration of B over time. Now, when you first look at this, you may think, wait a minute, that means that A is reacting half as fast as B, right? Which is not true at all. Right? It's reacting twice as fast. But let's say, for example, that this rate is 1, okay? 1/2 of 1 is 1/2. And so if the rate for A is 1, the rate for B is 1/2, and it is in fact reacting twice as quickly, right? The first time you look at something like this, it looks like the rate for A is half as much as the rate for B, but really it means that the rate is twice as much when you do the algebra associated with it. Okay. So let me get rid of that line. And then I'm going to write another generic, larger generic reaction here. So if I have A moles of A and B moles of B, going to form C moles of C and D moles of D. We're going to see this reaction a lot this semester. My rate is equal to negative for my products 1 over little a times the change in concentration of A over time, which also must be equal to negative 1 over little b times the change in concentration of B over time, which must also be equal to positive 1 over little c. Now we're in products, so they're positive. Change in concentration over time. And that has to be equal to 1 over little d, change in concentration of D over time. And so we can't have one product, one reactant reacting away faster than the products are being made. And so all of these rates are tied together. All of these rates are interconnected. All right, so using that information, let's do an example real quick. We need some rate expressions for these reactions in terms of the appearance and disappearance of the products and reactants. Right? And so the equation that we just looked at, write it out for these two reactants. Okay? Like I said, I'm going to give you a minute to work on that by yourself, and then I'll jump in and write it out. Because the coefficients are all 1 in that first one, it's pretty straightforward. You don't have to worry about those coefficients. For the second one, we need a few fractions there. So 1 over 4. One over 5. One over 4. One over 6. So again, we just take those coefficients and drop those down into fractions, and then those rates are all equal to one another. Right? Negatives for our reactants, positives for our products. Okay. All right, so let's put some numbers in here. Right? So let's say, for example, that we have this reaction, and at some moment, at a snapshot in time, we have an instantaneous rate of 0.024 molar per second. 0.024 molar per second. Well, in order to know the rate that N2O5 is being formed, which is our first question, we really need to know the relationship between these rates. And so let's go ahead and write out the overall rate expression. Okay. Now we have the overall rate expression. What we need to do is we need to pull out the pieces that are of interest to us for part A. For part A, we need to know the rate of N2O5, dinitrogen pentoxide, being formed. And what we know, the only one that we know is that oxygen, molecular oxygen, is a reaction rate of 0.024 molar per second. So now is that reaction rate positive or negative, right? Is that oxygen being used up, or is that oxygen being formed? Yeah, it's negative because it's being used up. And so this rate over here on the left, right, this is the thing that should always be positive. And so this rate is negative. The rate for just oxygen is a negative value. And that's why this negative in front cancels it out, right? So this plus this cancel out to give us a positive. Right? So I'm going to write this down here. Negative 0.024 molar per second is equal to 1/2 delta N2O5 over delta T. And so again, the rate for oxygen, because oxygen is a reactant, this is negative. Since O2 is a reactant. And the negative sign that we put in the rate expression cancels that out, so we get a positive number. So here's the negative sign for the rate expression, this first one. The negative sign from the fact that it's going away is the second one. Of course, those cancel out to give us a positive value. I'm going to multiply both sides by 2 to get rid of that 1/2, and I end up with 0.048 molar per second is this rate, this change in N2O5 over time. Any questions about that? I know that these positives and negatives can get a little confusing, but any questions about how we came up with that? Hearing none, let's go ahead and put this in for B. So we know that the same thing, 0.024 molar per second is equal to negative 1/4. That's our coefficient for NO2. different time. And so we would end up with this rate being negative 0.096 molar per second. That totally makes sense. NO2 is a reactant, it's being used up, so the rate for that should be negative. Right? Yeah. Any questions about that? Okay, so that's using this rate expression to move between reactants and products in the same reaction. Right? So I mentioned briefly that rate constant, and we talked about how we calculate that rate constant. And so we're going to go back there and we're going to talk a little bit more about that. And we're going to look at what is called the rate law. And so this rate law expresses the relationship between the rate and the concentrations of the reactants. Okay. Expresses the relationship between the rate and the concentrations of the reactants. Why don't we care about the products? I hear you cry. Okay. The reason that we don't really care about the concentration of the products is because in order for the reaction to move forward, having more or less products doesn't really matter. It's having more or less reactant. Those reactants reacting are what move a reaction forward. It's not the products sitting there being products, unless there's an equilibrium, which we'll get to in chapter 14. But generally speaking, this rate law, we're looking at things that are moving in one direction, and we're looking at how those reactants react together in order for that reaction to proceed. Okay, and so the rate, we've seen this already, but the rate is equal to this rate constant K times A to some power X and B to some power Y, right? So remember, this is from our generic A moles of A plus B moles of B give us C moles of C and D moles of D, right? So A and B are both reactants. This X and Y are not related to the coefficients little a and little b, right? Otherwise, it would have put little a and little b. When we read a rate law like this, we would say that the reaction is xth order in A and yth order in B, right? So let's say X is equal to 1 and Y is equal to 2, just for example, right? It would be first order in A and second order in B, and it would be third order overall. So again, if X was equal to 1, Y was equal to 2, it'd be first order in A, second order in B, and third order overall. Okay. So how in the world do we figure this out? How do we determine whether or not our rate law, our reaction is first or second order, third order, fourth order. How do we determine this, right? Well, we have to have data. And so rate laws are always experimentally determined. So let me write that over here. Always experimentally determined. Okay. You have to have some data in order to figure out the rate for a particular reaction. Okay. And so for this, what would the rate law look like? You can leave it in terms of x, but the rate is equal to k times what? That's my first variable.
One.
Concentration of F2.
Yeah, so concentration of F2 is my A, right? And I'm just going to put to the xth power. We don't know what it is yet. And then I need my B. That's ClO2 raised to the yth power. We don't know x and y, so let's figure those out. The way we figure it out is we look at a pair of reactions where, let's say we're interested in F2. We want to look at a pair of reactions where F2, the concentration of F2 changes, but the concentration of this ClO2 does not change. And so let's look. It looks like for 1 and 3, the concentration of F2 changes, but the concentration of ClO2 does not change. And so we're going to look at those rates. Right? So for F2, here's the way I think about it. For me, once you do this a couple times, it can get pretty straightforward. What happens to the concentration of F2? It doubles. Right? What happens to the rate? It also doubles. Right? And so for the concentration and the rate, they both double. What that means is if the concentration and the rate change the same factor, change by the same factor, then it is first order in that reactant. So I kind of think about it this way. Concentration doubles. And so the factor for the concentration is 2, right? It multiplied by 2. The rate is also 2. And then that's my x, right? So 2 equals 2 to the x. And if 2 is equal to 2, then x is just 1. So first order. How about for ClO2? Let me change colors here. We want to choose a pair where F2 is constant and ClO2 changes. And there's our rate. What happens to the concentration of ClO2? Goes up by a factor of?
4.
Goes up by a factor of 4. What happens to the rate between experiment 1 and 2 here? Goes up by a factor of 4 to the y. And so y must also equal 1. And so my overall rate law for this reaction is K times F2 to the first power ClO2 to the first power. Now I'm not quite done because I have two variables still. Right? Well, I need to know what K is, right? So we need to solve for K. And we can do that using any one of these experiments. And so I'm just going to use that top experiment, right? The rate is 1.2 times 10 to the negative 3 molar per second. That's equal to K times 0.10 molar times 0.10 molar. So I just solve for K. Oops. I'm not going to put it in scientific notation. 0.12. Now my units. Units change based on the order. And so if my rate is molar per second, and I'm dividing by molar times molar, or molar squared, then I end up with just a 1 on top, and then a molar and a seconds on the bottom. And so you can write this as 1 over molar seconds, or per molar per second that way. Our textbook tends to do the raise it to the negative first exponent. Okay. All right, so when thinking about rate laws, the rate laws are always determined experimentally. You will always have to have a table similar to the one on the last slide in order to figure out the rate law for a particular reaction. Okay? The reaction order is always given in terms of the reactants, right? The reactants are what are reacting, and so that's what we care about in our reaction to determine rate. Okay? And then last, the order of the reactant is not related to the stoichiometric coefficient of that reactant in the balanced chemical equation. So in the reaction we just did, F2 plus 2 ClO2 gives us 2 FClO2. It is true that the order for F2 was 1, and the coefficient for F2 in the reaction is 1. Just a coincidence, though. If we look at ClO2, the order for ClO2 is 1, but the coefficient for ClO2 is 2. And so the reaction order is not related to that stoichiometric coefficient. So let's end with an example. Here we have this reaction of nitric oxide with hydrogen. We're given the following experiments, and we need to determine how those, we need to determine the rate law and the rate constant, and then it asks us to go ahead and solve for the rate given a certain set of concentrations. So it looks like we've got 4 minutes left. I'm going to let you work for a couple of those minutes, and then I'll go ahead and start writing things out. So because the concentration doubled for NO and the rate quadrupled. Now, 1.3 times 4 is 5.2, right? That's pretty close, and that's close enough for us, especially given that it's only 2 sig figs, right? And so we're going to say that the rate quadrupled and that the concentration doubled. And so we end up with the rate being K times NO, sorry, it's just NO, NO squared times H2. And if we plug in one of these, 10.0 times 10 to the negative 5 molar per second equals K times 10.0 times 10 to the negative 3 molar squared times 4.0 times 10 to the negative 3 molar. We get our K value. Now we have molar per second divided by molar cubed. And so now we get 2 concentration units on the denominator. And so 1E4 divided by so we get a rate constant of 250 per mole squared per second. All right, well, we'll finish up this example on Friday. And like I said, going to edit the ALEKS things. Didn't get quite as far as I had predicted. And so I'll take away a few of our ALEKS topics from today for Friday. So do double check, make sure that you have everything completed if you were one of those who had already done all their ALEKS. All right, I'm going to go ahead and stop this recording and make sure it gets uploaded to our Moodle as well.